Welcome back to this next video in which we are discussing polynomial rings. Okay, so we've now defined how multiplication is going to work in this set of polynomials, and we're just in the process of making sure that it obeys the necessary axioms in order for our set of polynomials to actually be elevated up to the stature of a ring. Okay, so we've checked closure and we've checked associativity now. Let's move on to axiom number 3. So axiom number 3 that multiplication needs to obey is that it needs to have a multiplicative identity. We need a polynomial which will multiply by all other polynomials to give that same polynomial back again. Okay, so what is going to be our multiplicative identity? Well, it's going to be a monomial, and it's going to be a very special monomial. It's going to be the monomial which has the coefficient 1 in front of the power of x, x0. Okay, so more commonly we would just write this 1 like so. So it's the polynomial where all the other coefficients in front of all the other powers of x are going to be equal to 0, but in front of the first power of x, x to the power of 0, we will have the multiplicative identity from our original commutative ring R. Okay, now let's just think about why this will multiply with any other polynomial to give that other polynomial back again. Okay, so we'll check it one way round, but the exact same argument will work the other way round too. So if we consider this polynomial 1 multiplied by some other polynomial, okay, so we'll have our other polynomial here, the sum over I of ai x to the I, like so. Okay, and again, view this in the way of, originally view it in the way of just being a symbol, but in order to actually compute this multiplication, what we'll do is we'll reinterpret this as actually being a sum of monomials. And then if we want to multiply this polynomial, which is just a simple monomial, with this polynomial, we split this into its sum of monomials, and then we'll just multiply this with all of the monomials in turn. Now when we multiply this one monomial with all of the monomials in turn, we will multiply the two coefficients, and when we multiply the coefficients, of course 1 will multiply with any coefficient just to give that coefficient back again, and then we'll add the powers of x, but this is x to the 0. Okay, so that will add to all the powers of x just to leave the powers of x unchanged. So I hope you'll agree that what you'll get is just the sum over I of all the monomials unchanged, ai x to the I, and of course when you actually perform that sum you'll get back the same starting symbol in the set of polynomials that we started off with. Okay, and the same will be true if you do it the other way around. So if you swap these two around and have this on the left hand side and 1 on the right hand side, the exact same will be true. Okay, so this monomial where we have 1 in front of x to the power of 0 and then 0 in front of everything else, that polynomial in our set of polynomials is going to be the multiplicative identity in our polynomial ring. Okay, so that's axiom number 3, nice and easy. Axiom number 4 now, this one's going to be a bit more difficult. Distributivity. Okay, now we will check left distributivity, we will not check right distributivity because the argument will be utterly identical, just with a tiny little tweak. And anyway, we're going to check commutativity, and if commutativity is true and the left distributivity is true, you can always say that right distributivity will be true anyway. So we won't bother checking both left and right distributivity, but we will check left distributivity. Okay, right. So what we want to show then is that if we have a polynomial, okay, so I'll write a polynomial like so, sum over I, ai, xi, and we multiply this, and I might just put some square brackets here, we multiply this with the polynomial b plus the polynomial c, so we've got a polynomial b here, bj, xj, like so, and I might have over bracketed this a bit, but never mind. Okay, so here's our polynomial b plus the polynomial c, like so, so ck, xk, like so. I want to prove that if we do it this way, which means add these two polynomials first, get an answer, and then multiply it by this polynomial, that it gives the exact same answer as if I do it this other way. So firstly we multiply the two polynomials, so here is our polynomial a multiplied with our polynomial b. Okay, so we multiply a and b together, like so, and we multiply a and c together, so we'll have the polynomial a here, sum over I, ai, xi multiplied by the polynomial c here, the sum over k ck x to the k here. Okay, so I want to prove that if we do it this way, where we firstly multiply both of these polynomials by the polynomial a and then add them together afterwards, that the answer that we'll get, the overall answer, is exactly the same. Okay, so as always, the way that we're going to do this is we're just going to do both sides and show that the answer is going to be the same. And again, it's going to be most helpful, it's going to be easiest to do it in terms of turquoise here rather than in terms of red. Okay, so we'll get formulas like this where you could get the final answer just by summing up all the monomials, and we'll prove that the sum we'd get here is exactly the same as the sum we'd get here, and hence if you were to actually work out the final answer, you'd get the exact same thing. Okay, so I might have to get another piece of paper then to do this, which is a shame that I bothered to write that out there, but never mind. Okay, I might try and put it like this. Okay, so let's firstly take the left-hand side then here. Okay, so if we do the left-hand side, we want to add these two things first. Okay, so let's make the index the same here. So let me get rid of the k here, and we'll now have the index j. That's the first step to doing this. So I've just changed the index so that I can now combine these more naturally. Okay, so when I add those two together, all I'm going to do then is add the coefficients in front of all of the monomials in my original ring, capital R. So what I'll end up with then is something of this form: the sum over j of bj plus cj times x to the j. Okay, so I'll remind you that that addition there is addition in our ring, capital R, the original commutative ring that we had. And now what we're going to do is multiply this with this other polynomial, the a polynomial here, sum over I, ai, xi. Okay, so I want to multiply this with this. So how do I do that? Well, of course, I now stop viewing these as just abstract symbols. Instead, what I'm going to do is decompose them into their monomial sums. Okay, so I view this now as a sum of monomials, and I view this as a sum of monomials, and then I multiply all combinations of monomials together and sum them all up using my addition on the ring of polynomials, and then in principle I could go from that to an actual abstract symbol again. Okay, right, so this would be the sum over all I, sum over all j, and then we'd multiply the two coefficients together, so we get ai times bj plus cj. Okay, now understand this addition and this multiplication, that's all done in the ring, and you might be guessing what's going to happen here. This is going to actually just rely on distributivity holding in the original commutative ring. Okay, and we're just going to apply distributivity to that, but we'll see that in a moment. And then we'll get x to the I plus j. Okay, so if you were to perform that massive great sum here of all of those monomials in our ring of polynomials with the addition law that I've defined on it, then you would eventually get the answer. Okay, so what we're now going to do is do the same thing for the pink side here, the right-hand side of the equation. We're going to get a great big sum of monomials like this and show that all of the monomials that we're adding together are going to be exactly the same. Okay, so here we need to multiply both of these, or perform both of these multiplications first. Okay, so now let me write this here. So firstly, multiplying these two together, of course what we now need to do is decompose this into its monomial sum, decompose this into its monomial sum, and then multiply all of the monomials in the way that we've defined, and what we'll end up with is the sum over I, the sum over j, ai multiplied by bj, where that multiplication is done in the original commutative ring, capital R, and then we'll have x to the power of I plus j, like so. Okay, so again, this is a great big sum of monomials, and if you were to add all of those monomials up in the set of polynomials with the addition law that I've defined, you would eventually get the answer to what the polynomial a multiplied by the polynomial b is equal to. Okay, so that's this side here. Then what we're going to do is add this onto, and this addition, remember here, this addition is done in my set of polynomials, so I'm going to now add this onto the answer to this. Okay, right, so let's now do the answer to this one. Again, I'll decompose both of them into their monomial sums, and then what I'll do is multiply all the monomials together and then just add them all up. So I'll get the sum over I, and I'm going to change my index here. I'm going to get rid of that silly k index here and replace it with a j index, just being fortuitous, okay, because we're going to want to combine these two together, so let's just get rid of the k index and replace it with a j index. It doesn't matter after all. Okay, the sum over I, the sum over j, and then we'll have ai multiplied by cj, where that multiplication is done in the ring, capital R, and then we'll have x to the power of I plus j, like so. Okay, and again, this is a great big sum of monomials, and if you were to actually perform this great big sum of monomials using the addition that we've already defined for the set of polynomials, you would get a final polynomial which would be your answer to what the polynomial a multiplied by the polynomial c is. Okay, so if I now want to add these two polynomials together, I've got this one represented as a great big monomial sum, I've got this one represented as a great big monomial sum. If I just add those sums together, of course, I will end up getting the answer, basically. And what's nice here is that I've got the equivalent powers of x here. I'm going through all i's and all j's, and I've got all the same powers of x. So if I want to add these two things together, I can just add the components here. So this will just become the sum over I, the sum over j of, and then we'll have ai bj plus ai cj times x to the I plus j. Okay, so I'm just adding these two together. I'm just adding corresponding monomials together. Monomials that are obviously very much so linked and can be linked here. Okay, so I'm just adding those two together before I then do the final sum of monomials. So effectively I've just taken these two sums and combined them together, but that's perfectly valid to do. Okay, and what I've got here now, these multiplications and this addition, this is done in the ring, okay, because I've added these two together, and the way that you add two polynomials together, or two monomials in this case, we're adding monomials together, is you do just add the coefficients of those in the ring, okay, in the original commutative ring, capital R. Okay, so I hope it's clear what I've done there. I'm saying I've got analogous monomials in both of these sums. Let's add the two monomials together. How do I add monomials together? Using the addition law that I've defined for my set of polynomials, and that involves adding the coefficients together in the ring. And then what I'll have to do to finally get the answer here is just sum all of these monomials that I've finally got here up, again using the addition law that I've defined on the set of all polynomials. Okay, so here's my answer, the sum over I, the sum over j of ai bj plus ai cj, x to the I plus j. Okay, and hopefully you agree that if I perform this sum, which is the answer to the, is this all visible on here? Yes, I think so. If I perform this sum here, which is the answer to pink here, and if I perform this sum here, which is the answer to green up here, then those are going to give me the exact same answer. Why are they going to give me the exact same answer? Well, because all of the monomials that I'm adding here have got exactly the same coefficients as the monomials over here, because distributivity applies in the ring capital R, the original ring. So in the ring capital R, this coefficient in front of each of these monomials is identical to this coefficient over here. Okay, so in fact I'm adding up the exact same combination of monomials, and when you do add up the exact same combination of monomials, you're going to get the exact same overall polynomial as your answer, and therefore those two different ways of doing this are going to be identical, and distributivity will hold in our polynomial ring. Okay, so this is left distributivity. You could do the exact same argument with a few little tweaks to prove right distributivity for this set of polynomials, but we don't need to, because we're about to prove commutativity, and as soon as commutativity is true, right distributivity follows from left distributivity anyway. Okay, so let's now prove commutativity then. Okay, so commutativity then, what we want to prove is that it doesn't matter what order we multiply two polynomials together in. Okay, so let's have a look at this. So I want to prove that if I have two polynomials multiplied together, so here it's one polynomial, the sum over I, ai, xi, and here's another polynomial, the sum over j, bj, xj, I want to prove that it's the same as if I do it the other way around. So if I do the sum over j, bj, xj, times the sum over I, ai, xi. Okay, now why is that true? Well, again, we can multiply these two polynomials together by taking their monomial decomposition, their decomposition into a sum of monomials. Okay, so the answer to the left-hand side here is just going to be the sum over I, the sum over j of all of the monomials multiplied together, sorry. So you'll have ai times bj when they're multiplied together in the original commutative ring R, and then you add the powers of x to get x to the I plus j. Okay, so that's going to be the answer to the left-hand side here. Now let's consider what the answer to the right-hand side is going to be here. So again, we'll decompose this into a monomial sum, we'll decompose this into a monomial sum, we'll get the exact same combinations of monomials multiplied together, but of course they'll just be multiplied together in the opposite order this time, because this one's in the front and this one's in the back. So it'll again just be the sum over j, sum over I, bj, ai, x to the I plus j. Okay, now it really doesn't matter that I've interchanged the order of the sums. We're still summing over all i's and all j's. Okay, that really doesn't matter. We're still going to end up with the same monomials being multiplied together overall. Okay, all that we need to worry about is, are the coefficients of these monomials exactly the same? Is bj ai the same as ai bj? Well, of course they're the same, because commutativity holds in our ring capital R. Okay, so because of commutativity in our original ring capital R, we can just interchange those around, and we'll end up with this being the exact same sum of monomials as we've got over here. We'll have all the same monomials, we're summing them all together to get the final answer to what these two polynomials multiplied together is going to be equal to, and of course we will get the same answer doing it either way. So indeed, polynomial multiplication is going to obey commutativity. Okay, just a final comment then as to why, if we've got left distributivity and commutativity, we also have right distributivity. Okay, so if we've got left distributivity, we know that if we have a times b plus c, like so, it's the same as a times b plus a times c. Okay, we want to derive right distributivity from that, so if we consider b plus c times a, okay, we'd like to expand this in the way that right distributivity says. How can we do this? Well, because of commutativity, we can say that this is the same as a times b plus c. Okay, it doesn't matter what order we multiply things together in if we have the fact that commutativity is true. Okay, so that's a valid step. Then what we can do is apply left distributivity here to say that this is AB plus AC, and then we can apply commutativity of multiplication again to rewrite this as BA plus CA, so swapping both of these around. Okay, and again that's because of commutativity, and this is exactly what we'd like to expand this to. So I've taken this and turned it into this using commutativity and left distributivity. So if you do have left distributivity and commutativity, it implies right distributivity. Okay, so you might wonder why, when I initially did the definition of a ring, I stressed right distributivity as being separate to left distributivity. Well, if you remember, when we initially went through the definition of a ring in the video on definition of a ring, we did not insist that commutativity was obeyed. Okay, in the general ring, you don't need to have commutativity. A commutative ring will have this final axiom of multiplicative commutativity, but a general ring doesn't need to have commutativity. However, we still insist in a general ring that left distributivity and right distributivity must be true. And in the case that you don't have commutativity, you can't prove from left distributivity that right distributivity also follows, because as you see in this argument, we require commutativity. Okay, so in a general ring, you do need to state that you need both left distributivity and right distributivity. It's only if you're dealing with a commutative ring that the instant you've got left distributivity and commutativity, it implies you also have right distributivity. Okay, so that then concludes our discussion of polynomial rings. Okay, in this video we've seen the formal definition of a polynomial as just a symbol. We've then seen how once you've defined addition on the set of polynomials, you can go to a slightly more human definition of a polynomial, which is that the additions in between the terms actually do represent addition, because you can always decompose a polynomial into a sum of monomials. And then we've seen how we can define multiplication on this set of polynomials by defining multiplication of monomials and then just saying, okay, if there's a hope at all that distributivity is going to hold for this multiplication law, we need to have the case that if you're multiplying together two polynomials, you can decompose them into their monomial sums, and then the multiplication must just be expand those brackets in the natural way that distributivity says that you must be able to, and then multiply the monomials together and then sum them all up, and that must give you the answer as to what the two polynomials multiplied together is equal to. And we've seen that indeed it all does work and it does obey the axioms of a ring. Okay, so this structure now is a ring.